Hello, everyone. So let's remind ourselves about what we did last time. Basically, we used expected values, or as you know, another name for expected values is first moment, to derive lower bounds on Ramsey numbers. Okay, so if you remember, why did we use expected values? Because remember, the idea for this course is to show existence of certain structures by showing that the probability of existence of such structure in random constructions is positive. So we had to connect the concept of expected value to probabilities. I mean, a direct connection between these two, and that was provided by considering a specific random variable called indicator random variable. We saw that if we consider an indicator random variable, then the expected value will be expected value of, let's say, indicator random variable corresponding to event A is same as probability of event A. And just to remind you, indicator random variable for an event A is defined to be a random variable, meaning that it's a function from sample space to R, which assigns to elements of omega which are in A, assigns 1 to them, and assigns 0 to every other element of omega. So the output of indicator random variable is either 1 or 0. It will be 1 if the input is in event A, and if it will be 0 if the input is not in event A. Okay, so that's what we did last time. So today we want to look at tournaments and Hamiltonian paths. Okay, first let's see what is a tournament in graph theory. So definition, a tournament with n vertices is an orientation of the complete graph Kn. Okay, so imagine or consider a complete graph Kn where you have edges between any two vertices. Now, if I assign a direction to each edge, so normally when we talk about undirected graphs, you know, there is no direction, so there is just an edge between, for example, two vertices. But for directed graph, I can say the edge is from A to B or B to A. So once I assign direction to every edge in a complete graph, then that graph is called tournament. Okay, and what is a Hamiltonian path? The definition, a Hamiltonian path is a path in a tournament that passes through each vertex exactly once. Okay, just to give you an idea or maybe daily life example about this, tournaments and Hamiltonian paths? Well, of course, one application of tournament is in graph theory is just tournaments in, you know, sports. Let's say in football or volleyball, for example, let's say you want to conduct a tournament between 10 teams, for example, where any two teams has to play with each other. And how can we consider the direction here as an application here? So for example, let's say, you know, in football, for example, or I think many other sports as well, the games are, you know, home or away. So the teams could be home or the teams could be away. So let's say if the direction is from A to B, it could mean that, you know, the game is conducted so that team A is at home of team A and team B, for example, is away. Okay, so this could be an interpretation for a direction here. And then Hamiltonian path would mean that, you know, you want to conduct a tournament and like assign orders to the game. So which game should it be done first, which game second? So when you say, for example, A to B and then B to C, that means first the game A to B should be conducted and team A should be at home of team A and then team B should be away. And then B to C means that will be the second game. This time B is home and C is away, and then C to D and so on. So once we assign a Hamiltonian path, that gives an order in which we want to conduct the games. Okay, so let's look at an example first. Example, consider the following tournament with 5 teams or 5 vertices here. I mean, application could be teams, but here let me say vertices. With 5 vertices. How many Hamiltonian paths exist in this graph? Okay, so let me show you the tournament here. Okay, so this is the graph that we have. It's a directed complete graph, which means a tournament. Now we want to look at how many Hamiltonian paths this has. So we have to pass each vertex exactly once. Now, the first thing we want to notice is that if you look at C, vertex C here, so all the 4 edges ending up in C are towards C. So there is no way that we can go from C to anywhere. So we only have the option to go from somewhere to C, right? So that means that C could not happen in the beginning of the path because I cannot go from C to anywhere. C cannot happen in the middle either because again, I cannot go from C to anywhere. Only I can go from other places to C. So that means C has to appear at the end of my path. So the last vertex, okay? So I can say that there is no edge. Let me say C, the vertex C C has degree 0 out, it means there's no edge going out of C, all the edges go into C. So that means C must appear at the end of a Hamiltonian path, any Hamiltonian path in this tournament. Okay, so it's left to count how many paths we have from going through the remaining 4 vertices, A, B, E, and D. Now we must count the number of Hamiltonian paths, the number of Hamiltonian paths through A, B, D, and E. Okay, so far we have reduced the problem to finding a path passing through A, B, D, and E, which means the permutation of these 4 vertices, and there are 4 factorial or 24 ways to do that. But we can still reduce this problem further if we use the same idea. So basically, if we look, look at the vertex A, well, we know that, let's ignore the vertex C because we know that we have to put that vertex at the end. So we are left with 3 edges, A to B, D, and E. Now B to A, the edge is towards A, and then D to A also towards A. And therefore from A, we can only go to E. So what does that mean? That means that once I have vertex A appeared in my path, immediately after that, I need to have E, or another possibility is that I can have A at the end of my path, last vertex of my path. Of course, last vertex was C, but I mean among A, B, D, and E. A could be at the end, or could be immediately followed by E. So 6 again, so if A and E are together, it's going to be 3 factorial or 6 cases. And if A is at the end, again, another 6 cases. So we reduce the problem to only 12 possibilities. So let me write down. So similarly, there is only one edge out of vertex A. So this means A and E. A must be followed by E. By E. Or A can appear at the end as at the end of the path. I mean, again, end of the path, I mean, still ignoring C because we know that C is the last one of the path among A, B, D, E. Okay, so there are 12 possibilities. And by inspection, we can see that we have exactly 5 Hamiltonian paths. Hamiltonian paths, namely, okay, so there are only 12 possibilities. You can check them one by one, and you will see that we are left with either A, E, B, D, or BAED, or BDAE, or DAEB, or EBDA. So again, this is the tournament, and these are the possible paths. Of course, these are still ignoring C, so the final answer will be, lastly, this tournament has 5 Hamiltonian paths when the vertex C is added to the end of 5 paths above. So instead of, for example, AEBD, we should say AEBDC, and in BAEDC, and so on. Okay, so we gave an example of a tournament with 5 vertex, and which had 5 Hamiltonian paths. Okay, so now there is a theorem that says every tournament has at least one Hamiltonian path. Okay, so this is a standard theorem in graph theory. So I want to skip the proof because the proof, does not use probability, and our focus here is to use probabilistic method. So you can find this, in any standard graph theory book. So let's skip the proof of this. Now we want to mention a theorem that uses the probabilistic method. So another theorem. There exists a tournament. So let me say given an integer n. So for any integer n, there exists a tournament with n vertices that has at least n factorial over 2 to the power n minus 1 Hamiltonian paths. Hamiltonian paths. Okay, so let's say for any number n, there exists at least one tournament with n vertices that has at least n factorial over 2 to the power n minus 1 Hamiltonian paths. Now, the first question you can ask is that, can we say that, but we already know that every tournament has at least one Hamiltonian path. So do you think we can say that every tournament has at least n factorial over 2 to the power n minus 1 Hamiltonian paths? Because this theorem says there exists at least one tournament having at least this many Hamiltonian paths. But do you think we can say every tournament with n vertices has this many Hamiltonian paths? So question is, can we generalize this theorem to every tournament with n vertices? The answer is no. See example above. What did we prove just a few minutes ago? Let me explain this to you. We just provided an example of a tournament with 5 vertices that has exactly 5 Hamiltonian paths. Okay, but if n is 5, n factorial over 2 to the power n minus 1 will be bigger than even 7. So that means we cannot say that every tournament with n vertices has at least this many Hamiltonian paths, because for the example above with 5 vertices, the tournament did not have at least this many Hamiltonian paths. It only had 5 Hamiltonian paths. Okay, so now proof of theorem. Okay, I'm going to use 2 facts from, again, we're going to use expected values, which was the same idea as the last lecture, and also 2 facts that last time we mentioned. Let me again mention them briefly. Recall from last lecture that, so one fact was that P of x bigger than equal to mu was greater than 0, and P of x less than equal to mu is also greater than 0. Now this is exactly the typical result that we need in this course, probability of something greater than 0, and then that would prove the existence of the specific construction. And another thing was the relation between expected value and probability. So E of 1A is equal to probability of A, where 1A is the indicator random variable corresponding to an event A. Okay. All right, now let's go back to proof. Okay, to prove the theorem, let's remind ourselves about the idea that we follow in this course. And basically, we want to define an appropriate probability space and show that the probability that a randomly chosen element of this space has a desired property with positive probability, and then that will show or prove the existence of the construction that we need. So here, basically, we want to show that there exists at least at least one tournament with n vertices that has this many Hamiltonian paths. So basically, if I show that probability that at least this many Hamiltonian paths exist is positive in a randomly oriented complete graph, which means a tournament, random tournament, then it will prove what I need, okay? So the idea, I can say, idea is to prove probability that at least n factorial over 2 to the power n minus 1 Hamiltonian paths exist in a randomly oriented complete graph K. To do so, consider a randomly oriented complete graph Kn. Randomly oriented means randomly oriented complete graph Kn means random basically tournament. So just reminding that the complete graph Kn, once the oriented complete graph Kn is a tournament, and note that each Hamiltonian path corresponds to a permutation of 1 to n. See, Hamiltonian path means what? Means we have to pass through each vertex only exactly once and with a direction. So we can go from 1 to 5, then for example 5 to 7, 7 to 9. So if we like put these numbers next to each other, let's say 1, 5, 7, 9, you know, then for example 8. So I will have a permutation of 1 to n, right? So I go from 1 to another vertex, then second vertex to third vertex to fourth vertex, and then all the way to nth vertex. So I will have a permutation for each Hamiltonian path. I will have a permutation of 1 to n. Okay, so let me give you an example. For example, if the Hamiltonian path is, for example, let's say 1 to 3, 3 to 4, 4 to 5, to 7, 7 to 6, 6 to 2, then this corresponds to, then it corresponds to 1, 3, 4, 5, 7, 6, 2, which is a permutation of 1 to 7. This is a permutation of 1 to 7, right? Where 1 goes to 3, 3 goes to 4, 4 goes to 5, 5 goes to 7, 7 goes to 6, 6 goes to 2, and 2 goes to 1. This is a permutation by definition of permutation. Okay. So we established that each Hamiltonian path corresponds to a permutation of 1 to n. Okay, now fix a permutation sigma of 1 to n and let x sub sigma be the indicator and the variable of existence of the Hamiltonian path indicator and the variable for existence of the Hamiltonian path, let's say sigma 1, sigma 2 to sigma n. So we look at because random variable is a function from sample space to R. For indicator random variables from sample space to 0 and 1. So we look at I look at the element of my sample space, which is a randomly oriented complete graph. So I look at it. If it has this Hamiltonian path, remember again, each Hamiltonian path corresponds to can be written as a permutation. If it has this, I look at the element of sample space, which is a oriented complete graph. If it contains this Hamiltonian path, then this random variable assigns 1 to that element of sample space, otherwise it assigns 0. Okay. So how much is the expected value? Then what is the expected value of this random variable? So let's look at the expected value of this random variable. Then expected value of x sub sigma is probability. Okay, this is important. See, I reminded you in the beginning of the proof, expected value of an indicator random variable is probability of A. Indicator random variable corresponding to event A. Now, what is our event here? Probability of event A, where A is the event at the edges sigma 1, sigma 2, sigma 2, sigma 3, sigma n minus 1, sigma n, are all included in a random oriented complete graph. My event here is that what is the event is desired possibility, all the desired possibility. What is my desired possibility here? My desired possibility is that if all these edges are included in my randomly chosen element, randomly oriented complete graph, because in that case, I can say that the Hamiltonian path corresponding to this permutation exists in my tournament. So the event here, which is my desirable property, is the existence of all these edges with this order. Remember that the order is important here because we're talking about oriented graphs. So I want sigma 1, sigma 2 to be in my graph, sigma 2, sigma 3, all the way to sigma n minus 1 and sigma n. And what is the probability of this happening? So note probability of A is equal to probability that sigma 1, sigma 2 belongs to, let's say, E. If I call E as the set of all edges, all oriented edges, sigma 2, sigma 3 is in E, all the way to sigma n minus 1, sigma n. Now I'm assuming that I'm assigning orientations to my edges randomly and independently. So I can say that the probability that each of these edges exist is the multiplication of the probability. So this is same as probability that sigma 1, sigma 2 is in E times probability of sigma 2, sigma 3 is in E all the way to probability times probability that sigma n minus 1, sigma n is in E. Okay, so remember that if let's say A1 and A2 are independent, probability that A1 intersection A2 is P of A1 times P of A2. And here I'm assigning orientation to my edges independent of each other. Now, what is probability that sigma 1, sigma 2 is in E? Well, sigma 1 and sigma 2 are just two numbers between 1 to n. Let's say, for example, there are 5 and 8. So what is the probability that I have an edge from 5 to 8? But we are talking about a complete graph. So there is edge between any two vertices. So between vertex 5 and 8, I definitely must have an edge, but either from 5 to 8 or 8 to 5. So the existence of edge between 5 to 8 is true for sure, but the orientation could be from 5 to 8 or from 8 to 5. And I'm assigning the orientation randomly. So by probability, with probability 1/2 is from 5 to 8. Again, probability 1/2 is from 8 to 5. So probability sigma 1 and sigma 2 is in E is 1/2, because again, with probability 1/2, I have sigma 2 and sigma 1 in E. So the first number is 1/2, then times 1/2, all the way times 1/2. How many 1/2s do I have? So one term, two term, all the way to n minus 1 term. So it's 1/2 to power n minus 1. So we show that E of x sigma is equal to 1/2 to power n minus 1. Okay, so this one, what was E of x sigma? I fixed my permutation and I found the expected value. Now, if I want to, so let's say if I want to know whether in a randomly chosen orientation, whether the Hamiltonian path corresponds to the permutation sigma exists or no, I can consider x sigma. If x sigma is 1, that means the Hamiltonian path exists. If it's 0, it means it does not exist. Now, if I want to look at all the permutations, all the Hamiltonian paths corresponding to all permutations, I can simply consider x sigma 1, x sigma 2, so all the permutations from 1 to n, and the indicator random variables, and I add them. Okay, so let me write down this for you. Next, consider all permutations of 1 to n, namely, okay, so I'm sure you know how many permutations we have for the set 1 to n. There are, of course, n factorial such permutations. So namely sigma 1, sigma 2, all the way to sigma n factorial. So there are n factorial such permutations, and consider the random variable x to be x sub sigma 1 plus x sub sigma 2 all the way to x sub sigma n factorial. Look at this random variable, capital X. It's addition of few other random variables. Now, what does x sigma 1 do? If x sigma 1 is 1, then it means that I have the Hamiltonian path corresponding to sigma 1 in my randomly chosen oriented graph. Similarly, same thing for x sigma 2, same thing for x sigma n factorial. So when I add them, so if, for example, capital X is 5, that means 5 of these X sigma i's are 1 and the rest are 0. Because remember, each X sigma I is either 1 or 0. So if capital X, which is addition of them, for example, is 5, that means 5 of these X sigma i's are 1 and the rest of them are 0. And that would mean I would have exactly 5 Hamiltonian paths corresponding to 5 permutations. Similarly, if capital X is 6, that means I have 6 Hamiltonian paths corresponding to 6 permutations. So basically, this capital X measures the number of Hamiltonian paths. And of course, again, each Hamiltonian path corresponds to 1 permutation, 6. So this X measures total number of Hamiltonian paths in a randomly oriented complete graph Kn. And note that how much is E of X? Expected value of X is expected value X sigma 1 plus expected value of X sigma 2 all the way to expected value of X sigma n factorial. Okay, so each of these ones we already showed that because we said if I fix any permutation, E of X sigma is 1 over 2 to the power n minus 1. So this is going to be 1 over 2 to the power n minus 1 plus 1 over 2 to the power n minus 1 all the way to 1 over 2 to the power n minus 1. So this is n factorial over 2 to the power n minus 1. Okay, so that means lastly, P of X bigger than equal to E of X is positive. This is the remark that I just said before starting the proof, and we also used this last time. We proved this actually last time as well, also used it last time. So this means that P of X bigger than equal to n factorial over 2 to the power n minus 1 is positive. So that means with positive probability, X, which is the total number of Hamiltonian paths, is at least n factorial over 2 to the power n minus 1 in a randomly oriented complete graph. So that means at least one of those randomly oriented complete graphs has at least this many Hamiltonian paths. So that means there exists a randomly oriented complete graph Kn, again, i.e. a tournament with at least n factorial over 2 to the power n minus 1 Hamiltonian paths. Okay, so if I want to summarize how we proved this result, one key result was that each Hamiltonian path corresponds to a permutation. And we know how many permutations we have 1 to n, and that helped. Another important fact was that expected value of an indicator random variable corresponding to an event A is probability of that event. And we could easily find probability of the event because we were assigning orientation to each edge randomly and independently. So we just multiplied the probabilities and each of them were 1/2. And finally, we use the fact that probability that X is bigger than or equal to mu is positive. So once we show probability is positive, similar to previous lectures, the existence of the construction that we're looking for was proved. All right, so I think this much is enough for today. Thank you so much and see you soon.